Why does a battery that says 12 volts sometimes only deliver 11 volts? And what is a battery actually doing inside of a circuit? In this video, we'll look at EMF, internal resistance, and the actual path current takes in a real loop, as well as terminal voltage. So what's EMF? EMF, written as this symbol, stands for electromotive force, but it's not a force. The name is misleading. It is the energy delivered per charge, measured in volts. So if a battery has 12 V EMF, it gives 12 joules of energy per 1 coulomb of charge that passes through it. It's what powers your phone, your lights, and your circuits. Let's look at how a battery is drawn. So in the topic of DC circuits and electricity in general, you will see a lot of this stuff and these kind of diagrams. And this is new on the channel. I haven't covered this stuff at all. So I'll make sure that you understand it as good as possible and that every new symbol on these diagrams is explained. And you don't have to understand every part of every diagram 100% as we go through, because when we do more problems, your brain will start to piece it together and will understand it. And I'll make sure of that. So in a battery, for these kind of circuit diagrams, a battery is represented like this. What is that? The long line here is a positive terminal. The short line is a negative one. The gap between is not literal. There's not an actual physical gap in the battery. It's just a visual placeholder for us people analyzing the diagram that represents the chemical reactions that give energy. So when you see this symbol, just think this is the push. This is where charges get their energy. And the EMF is here. Real batteries are not perfect. Inside of a battery, there's something called internal resistance, which we call R. Even before the current reaches your circuit, some of the energy is lost inside of the battery because of, for example, friction in the electrolyte, which is the fluid that connects the two terminals. It might be sluggish chemistry or imperfect electrodes. Because in real life, things are not perfect. So while your car battery might be labeled 12 volts, but when you turn on the car, which is a high current activity, it might drop to 10.5 volts because of the internal resistance. This 12 volts would be the ideal voltage, aka the EMF. And this is how we model internal resistance. So we might have point A, the internal resistance here, and the battery, or the EMF point, and point B. And it might wrap around and hit an external resistor labeled R. What's going on? Our current, this is negative, this is positive, our current is going to travel clockwise like that. Then you might think, but aren't these the terminals? Well, let me explain. First, before we walk the full circuit path, step by step, let me go through some vocab. What does in series mean? So you're going to hear words like series and parallel in this topic. When things are in series, it just means they're next to each other and the same current flows through them. You can imagine this like you have a battery and then you got a resistor here, another resistor, and you got something you're powering. If it's in series, then the same current flows through them one by one through each of the components in that exact order. And if you take one of these components out, the entire thing falls apart and no current will flow through. So here's what's happening in this diagram. Let's start at point A. This is the positive terminal, or the long line. The current flows upwards, it's clockwise. So it flows up here and hits this external resistor. Zigzag lines means a resistor. They control the amount of current going through. So this external resistor, we hit it, keep flowing through here. And now where are we? We've arrived at point B. Point B is the negative terminal of the battery. And then inside the battery, you're going to continue here through the EMF source, which is, let's just say 10 volts. And then through the internal resistance, which happens because of imperfections in battery. Some energy is lost here. And then you arrive back at point A, where you begin the entire loop all over again. And then happens. This is a circuit. And if you've been studying electricity, you might have noticed something weird. Why does our current go from negative to positive? The convention says that current goes from positive toward negative. So did we just not go backwards? Why is it this direction? So it might feel backwards that we're going from B to A. However, if you ever see like an internal current pointing upward, arrow like this telling where the current goes, this arrow only shows the internal section of the circuit inside the battery. Here's the logic. Outside of the battery, the current goes downhill from high potential to low potential. That's what a current follows. But inside the battery, the EMF lifts the charges back up. So it goes from low potential to high potential. Imagine like you have a boulder rolling downhill, and then inside the battery, your boulder gets energy to get pushed uphill again to restart the loop. Now, this is why the current flows clockwise, and inside the battery, the current is going backwards. So what's terminal voltage? The battery tries to supply the EMF amount of voltage. And that's the ideal voltage, but some of it gets lost inside the battery, going from one terminal to another because of the internal resistance. So the actual voltage delivered to the outside circuit, the actual energy being provided is terminal voltage, which is the ideal voltage minus the current times the internal resistance. What does this tell us? It tells us that the voltage you're actually getting depends on how much current you're drawing. So if you draw a lot of current, which gives you a big I, the voltage across the battery will drop. This is why your headlights dim when you start the car. And one last note before we go through an example problem. The order that we draw EMF and R actually doesn't matter. They're in series, so the voltage gain or the voltage loss is the same. Does this reverse the energy flow if we flip them around? No, the current still gains energy from the EMF and then loses it from the internal resistance. The physics is preserved. Here's the example problem. We're just going to use the same diagram because it works. The EMF is 9 volts. The internal resistance of the battery is 0.4 ohms. And the external resistor labeled big R is 45 ohms of resistance. Our goal is to find a few things. One is the current. Two is the terminal voltage. And the power losses in a battery with internal resistance. Let's start by finding the total resistance because that's going to help us find the current. So the total resistance is 45 ohms plus 0.4. It is 45.4 ohms in this circuit. The current in the circuit is given by EMF divided by the total resistance. And all of these formulas are on the free cheat sheet in the description, which is 9 volts divided by 45.4, which is roughly 0.198 amps. Okay, we just found the current. How about the terminal voltage? Terminal voltage is given with this formula, which is also on the free cheat sheet. It's the EMF minus current times internal resistance. So 9 for EMF minus current, we just found, times internal resistance, 0.4, which is roughly 8.92 voltage. So what does this number tell us? If this is the terminal voltage, it means the battery has lost some energy as it moves through the internal resistance because the ideal voltage was 9. How about if we wanted to find the power that's delivered to a circuit? The power that's delivered to a circuit is given with this formula, which we've looked at before. It's the current squared times R, which is 198 squared. This is our current in amps, multiplied by big R, the external resistance, 45, giving us roughly 1.76 watts of power delivered to a circuit. How about the amount of power that gets lost inside of the battery? And that happens from the internal resistance. So that would be current squared times internal resistance. Same thing, but instead of big R, we take the value of small r, 0.4, giving us roughly 0.016 watts of energy lost. The circuit still receives its 1.76 watts of power, and only this much is lost inside the battery. But that loss still matters in high draw circuits or when batteries are aging.